been learning about equilibrium and how in a dynamic equilibrium, the reaction proceeds in the forward direction and the reverse direction at the same time. Well, how can we predict which direction the overall reaction is going to go if it's not already at equilibrium? If we have non-equilibrium values for the reactants and the products, how can we tell, is it going to go forward or backward? And the reaction quotient is what will help us with that. So that's Q, capital Q, QC or QP. So this is calculated with concentrations, and this is calculated with partial pressures in atmosphere. And the reaction quotient is calculated in exactly the same way as we calculate the equilibrium constant. So there's our reaction, and this would be the expression. So how are they different? The equilibrium constant is at equilibrium. Q is when you calculate this any old time. So you can always calculate the reaction quotient. And then you compare the reaction quotient to the equilibrium constant. Because you know at equilibrium, they're going to be equal, right? So you can look at them and see, oh, well, it's smaller, I know it's going to go forward, or it's larger, I know it's going to go in the reverse direction. So here's a graph with far too much going on. Simple reaction, equilibrium between A and B. So the reaction quotient would be the concentration of B over the concentration of A. So what we're graphing here is the reaction quotient on the y-axis and concentrations on the x-axis. So here we're starting out with 1 molar A and no B. All reactants, no products. And as we go across, the reaction is occurring. Here we've got half of A has reacted, and so we've got half molar A and half molar B. And as we keep going across, now we've got more products and less reactants. Okay? So the equilibrium constant for this made-up reaction is 1.45. Why? I don't know. They just picked that. 1.45. So that says that at equilibrium, we could go down here and we could figure out what the concentrations are. But we can calculate the reaction quotient at any concentration. If we calculate it over here, where B is 0 and A is 1, well, 0 over 1 is going to give us a reaction quotient of 0, right? As we go this way, the reaction quotient is going to get larger and larger. Is it ever going to get to exactly 1? No, why not? It would be 1 over 0, right? And you can't divide by 0. So we see that this is going up, and they don't finish the graph. It's just going to keep going up. It's going to get super, super close, but yeah, never going to get all the way there. Okay, so if we look at this middle of the road thing, so I asked the wrong question. The question was not, well, the question I asked was, can Q be 1? And that's not the right question. Can we get to this point is what I meant to ask. And that's the question we answered. When we have equal concentrations of A and B, then Q is equal to 1. And so we can compare this reaction quotient of 1 to the equilibrium constant of 1.45. We know the reaction is going to proceed in a way that makes Q get closer to K. So here, Q is smaller than K. And so what's going to happen for Q to get larger? For Q to get larger, we have to get more products and fewer reactants. The reaction has to go forward. And so that will happen until it gets to equilibrium. If we start up here, where we've got 0.25 molar A and 0.75 molar B, Q is going to be, 2.5-ish? And that's larger than K. So Q is larger than K. What's going to bring Q down to K? To make Q smaller, we have to reduce the products and increase the reactants. Does that make sense? So the reaction is going to proceed in this direction. Any questions? So this is a summary, and you could memorize this. I wouldn't even try. Because larger, smaller, forward, back, how do you correlate those? You don't, right? You mix them up, especially when it's important. So when Q is smaller than K, the reaction is going to go to the right towards the products. Don't try to memorize that. Think about, well, if Q is too small, what's going to make it bigger? It's reactants over products. We need more products. I said that backwards. It's products over reactants. Just shoot me now. When Q is too small, we think, well, Q is products over reactions. If we need it to get bigger, we need more products. Reaction goes forward. If Q is larger than K, how can Q get smaller? Products go down, reactants go up. Reaction goes in reverse. Okay? And at equilibrium, Q is going to be equal to K. Okay? Okay. So at any given temperature, there is only one value for the equilibrium constant. There are many values for Q. You could say infinite within this range, right? It depends on the current state, and then it's going to be constantly changing. Okay, consider the reaction and its equilibrium constant. Reaction mixture contains NO2 and N2O4. Here are their concentrations. Calculate QC, determine the direction in which the reaction will proceed. So, to calculate QC, we write the same expression we would for the equilibrium constant. So, concentration of the products squared, because of the coefficient, divided by the concentration of the reactants. Okay? So here we're given concentrations. So we can just plug these into our little equation. NO2, 0.0255 squared. N2O4, 0.0331. Let me do some math. I did the math wrong. I left out a decimal point in the numerator. It matters. Let me try that again. Okay, that looks a little more reasonable. 0.0196. So that's the value of Q. And it says, determine the direction in which the reaction will proceed. They're giving us the equilibrium constant. They gave it to us in scientific notation. I happen to write this in decimal notation. So you have to be really careful when they're not in the same notation. So I would prefer to look at this one also in decimal notation. So which one's bigger? QC is bigger. So QC is bigger than K. The reaction is going to proceed in a way that makes QC get smaller. Forward or reverse? Reverse. So it's going to go in the reverse direction. It'll go this way. Any questions? same reaction. It says it initially contains both the reactant and the product in their standard states. So they are gases. For a gas, a standard state is a partial pressure of 1 atmosphere. If you need to review that, it's in section 7.9. If Kp is 0.15, which statement is true before any reaction occurs? So these are in their standard states, and Kp is 0.15. Does Q equal K? How would we calculate that? Well, it's NO2 squared over N2O4. They're both 1. 1 squared over 1 is 1. K is 0.15. They're not equal, right? So it's not the first choice. Is Q less than K? No, thank you. Q is greater than K. So Q being bigger than K tells us the reaction will proceed to the left. The numerator needs to get smaller, the denominator needs to get bigger in order for it to eventually become the same as K.